All right. So in this topic, you learn about binary trees, explore the various binary tree traversal algorithms, learn how to organize data in a binary search tree, discover how to insert and delete items in a binary search tree. First, what is a binary trees? So a binary tree, T is either empty or such that T has a special node called the root node. And T has two sets of nodes, the LT and RT. LT is the left subtree and RT is the right subtree of T. And of course, the left subtree and the right subtrees are binary trees, meaning it may have also the left subtree and the right subtree. So this figure shows a binary tree. So this is the left subtree of A, and this is the right subtree of A. Okay, and each of the subtrees is a binary tree in which nasa siya left subtree and right subtree. Okay? So this figure shows a binary tree with one node. Okay, there's only one node in this binary tree. The root node of this binary tree is A. And the left subtree of A and the right subtree of A are empty. Okay, since the left reference variables and the right reference variables are not pointing to a specific node. And this figure shows a binary tree with two nodes. And the right subtree of this binary tree is empty. Okay. And the left subtree of A is B. So this is a binary tree with two nodes, A and C. And the left subtree of A is empty. Okay, wait for a while. And this figure shows a various binary trees with three nodes. The first figure, we have the root node A, and it doesn't have the left subtree, but it only have the right subtree. And B doesn't have a right subtree, but it has a left subtree, which is D. The second figure shows a node with a left subtree, B and E, but it doesn't have a right subtree. Okay, so this is the left subtree of A. Okay, B is a binary tree without a left subtree, but it has a right subtree, which is E. Okay, then number 3, it's a binary tree with a root node A, which doesn't have a left subtree, but it has a right subtree. Okay, and this one, A is a root node without a left subtree, but it has a right subtree. Okay, C has a left subtree but doesn't have a right subtree. So in binary tree, we have here a collection of nodes. In each node, there is a data that is stored in a specific variable like info. And we have also two reference variables. Reference variable to the left child is stored in L-link. And R-link is a reference variable to the right child. Okay, just like this one, we have the binary tree that is the root node is A. Okay. I mean, the root node has an info A and has a reference variable, left link and right link. Left link is pointing to this binary tree through this node B. Okay? And the node of this, I mean the reference variable of the right link of this node A is pointing to this binary tree. Okay, so we have the following definitions of binary tree. We have here the leaf node and the parent node. The leaf node has no left and right children, and the parent node with at least one child node. So leaf node is a node that has no left and right children. Okay, so meaning the left reference variables and right reference variables are null. The parent node is a node in a binary tree with at least one child node. So pwede ang iyahang left subtree is empty and naa lang siya right subtree. So it's a parent node, or both naa siya left subtree and right subtree. And we have also the level of node. To know the level of node, we have to count the number of branches on the longest path from, I mean, the number of branches on the path from root to node. Say, for example, the level of G is the number of branches from root 1, 2, 3. So the level of G is 3. Okay, the level of C is how many number of branches starting from the root? We have 1. So the level of C is 1. Now, the height of a binary tree is the number of nodes on the longest path. That's not no, but on the longest path from root to node. Say, for this one, what is the height of this tree? Okay, which link, which is the highest? We have here the in this path, starting from root, we have 1, 2, 3, 4. So looking at this path, it is the the longest on the left side, but if you count also the right side, it's the same. So the height of this tree is 4. 1, 2, 3, 4. Okay. Okay, so this is the recursive algorithm to find the height of binary tree. So we have the height of P denotes the height of binary tree with root P. Okay, so we have if P is null, so our tree is empty. Else, height of P is equal to 1 plus the maximum height of P dot link and height of P dot R link. Okay, so we have the method max, predefined method max, to be used to get the maximum height of left and right subtrees. And we have 1 plus here since this one will be used to get the number of branches, and we'll be counting the number of nodes starting from the root maunang naatay 1 plus diri. Okay, so this is the method to be used to implement the previous algorithm. And we have also copy tree. Okay, so this operation is useful on binary trees to make the identical copy of binary tree. And this is useful in implementing copy constructor and the method copy tree. In binary tree, we have the different traversals. Okay, in traversing the binary tree, we must start traversing from the root. Why? We can access the binary tree through the root. Okay, so must start with the root, then visit the node first or visit the subtrees first. Subtrees is either you can choose on the left subtree or the right subtree. And we have here the different types of binary tree traversals: in order, pre-order, and post-order. For the in-order traversal, we have to traverse the left subtree first, then visit the node or the parent node, then traverse the right subtree. Again, for the in-order, it's left node right. Then the pre-order, we have to visit the node first, then traverse the left subtree, then traverse the right subtree. Then for the post-order traversal, okay, we have to traverse the left subtree first, then go to the right subtree, then visit the node. Okay, again, for the in order, it's left root right or left node right. For the pre-order, it's node left right. For the post order, left right root. Okay, so for these three traversals, it only differs on asa nahimutang ang info or the root node. Okay, or the parent node. So in the in-order traversal, the root node is placed at the center. The pre-order, the node or the root node is placed at the beginning. And the post order, the node or the root node is placed or is found at the end. Okay. So in this given binary tree figure, let us try to traverse using the in-order traversal. Okay. So we can access the tree using the root node A. Okay. So A has a left subtree, which is this one. Okay. B is a parent node. Okay, but doesn't have a left subtree. So since it doesn't have a left subtree, we will go to the node or the parent node, which is B. Okay. Then B has a right subtree, which is D. So put D. Next, we are done with this left subtree of A. So we'll go to the root, which is A. Okay. Next, we will go to the right subtree of A. In the right, it has the node C, but doesn't have a left subtree, so we have to put C. Its right is empty. So the in-order traversal of this binary tree is BDAC. Okay, that's in order. Okay. Now, let's try to traverse using pre-order. Ang sagal itong pre-order, it's root or node left, right. Okay. So in this case, we have A, which is the root node. So we have to put A. Then go to the left of A. So we have this subtree. Okay, its root is B. Okay, B doesn't have a left subtree, so we'll go to the right subtree, so which is D. So si D, wala man siya left and right subtree. So we are done with this node and the left subtree, A, B, D. Now let's go to the right of A, which is the parent or the node in the right subtree of A is C. So C is a leaf node. So that's the end. So the pre-order traversal of this binary tree is A, B, D, and C. Now for the post order, okay, for the post order, it can be traversed starting from the left, then go to the right, and go to the node. So left, right, node. So we'll go to the leftmost node of this binary tree. Okay. So B is a parent node, but doesn't have a left subtree. So we'll go to the right of B. So we have D. D doesn't have a left and right subtrees. So we'll put D. Okay. Then we are done with the right. We will go to the parent of D, which is B. Next, we are done with the left subtree of A. Kay left, right root man. Okay, left, right root or left, right node. We'll go to the right. So the right of A is C. C is a leaf node. So we will put C. And we're done with the right. So we'll go to the parent of this right subtree, which is A. Okay, so as you can see in the in-order traversal, the root node is found at the center. The pre-order is at the beginning and the post-order is at the end, ang root node. Okay, so using the recursive algorithm, we can implement the in-order, pre-order, and post-order in this way. Okay, so we have to have the reference variable of the binary tree node P. Okay, so this holds the address of the binary tree of the root node. Okay, so it will not stop if P is not equal to null. So while naapay sulod, wala pa naman og traverse. And we'll have to start traversing from the left for the in-order traversal. So that's why we have here in order that is calling this method and use the reference variable left link, that is to traverse the left subtree of P. Then we have here p.info, that is to print the info of each node, then go to the right link. Okay, reference variable of the right. Then for the pre-order, this is also the recursive algorithm. For the pre-order, we have to print the info first in each node, then go to the left link, then go to the right link. And for the post order, okay, so again, this is a recursive algorithm to traverse the binary tree using the post order traversal. That is, traverse the left subtree first using the L-link reference variable, and then go to the right subtree, then print the info, okay, using the p.info. Okay, now we have here the binary search trees. The binary search tree is a type of binary tree, but there is an organization of nodes. That is, the data in each node is larger than the data in its left child and smaller than the data in its right child. Okay? And the binary search tree, T is either empty or T has a special node called the root node. And T has also sets of nodes LT and RT called the left subtree and the right subtree. Okay? Key in root node is larger than every key in left subtree and smaller than every key in the right subtree. And of course, each of the left subtrees and right subtrees of this binary search tree must also apply the concept of binary search tree. I mean, the data in each left subtree and right subtree must be organized also. Okay, just like this one. We have a binary tree with 60 as our root node. Okay, 60. 60 is a root node, and the left subtree of 60 with nodes that are smaller than its parent. Okay, so 50 is a parent node and has a left subtree, which is this one. Okay? So, kailangan binary search tree gihapon ang left and right subtrees. So, 30 doesn't have a left subtree, but it has a right subtree, which is 46. So, take note, 46 is a right subtree, so must be greater than its root, which is 30, but lesser than the parent of 30, which is 50. Okay? So 50 has a right subtree, which is 58. Okay. So these are the nodes that belongs to the left subtree of 60. And they are smaller than 60. And the right subtree of 60 are these nodes. We have 70, 80, and 77. Okay, 70 is a parent node that doesn't have a left subtree, but it has a right subtree, which are 80 and 77. Okay, 80 has a left subtree, but doesn't have a right subtree. 77 is less than 80. And these nodes are greater than 70 since they belong to the right subtree of 70. Okay, so in this binary search trees, we have the organization of data. That is, the left subtree must be less than the parent node and the right subtree must be greater than the parent node. And of course, its children or uh, child subtrees must apply the concept of binary search tree. Okay? For binary search trees, we have also the following operations. Determine whether the binary search tree is empty. Okay, search the particular binary search tree for a particular item. Then insert an item in the binary search tree and delete an item from the binary search tree. And also find the height, find the number of nodes, find the number of leaves. How will you know that um, this node is a leaf node? If their left link and right link are null. Okay. And of course, traverse the binary search tree using in order, pre-order, and post-order, and copy binary search tree. Okay, so we have the figure of linear binary search trees. And the first one, it's linear to the right. And the second one is linear to the left. Okay, yeah, it so happen. It will happen if um, we have to implement the binary search trees. Yeah, di na malikayan that we can have the linear binary search trees. Okay, linear to the right and linear to the left. Okay, and for that, to balance the height of a binary tree, we have the ABL tree, which will be tackled after the binary search tree. Okay, and also a non-recursive traversals can be implemented for binary tree and also binary search trees. Okay, then maglisod ka. Is there are some movements for that nasad. If dili empty or dili leaf node ang imuhang right subtree. Okay? All right. So now, okay, for this binary tree, we have to create a class for the node. Okay, kay collection of nodes man siya. All right. Okay. So we will be creating a new project like this one is a binary tree. Okay. So you have to create a Java class for our node. We will name this one as BT node. Then in each node, we have the relevant info, like for this info, we'll receive a value of an integer. Then reference variables for the left node, I will call it left link and right link. Next, we will have the default constructor. Okay, for this default constructor, we will set the values for these three info, left link, and right link to its default values. an integer of info, okay, initially to 0, then left link to null, then right link to null. Okay. Then for the constructor with parameters, um, info, we'll organize na lang. The left link, the info, and the right link. Okay, so we'll set the values for this. Okay, using the this reference, the left link is equal to left link. And then the info is equal to right link. Okay, next, we can create the binary tree class. For the binary tree class, bt class. Okay. Maghimo na taog binary tree. So, how will you create a binary tree? How will you access? Of course, we need to have the reference variable that will point to the root node. So it is of type bt node called root. So this will point to the first node of our binary tree. Then, okay, later na lang to ang mga leaf, parent nodes, um, count of leaf nodes. So we'll have the um, default constructor. Next, we will set the root node to null. Next, um, the constructor with parameters and pass the root and this dot root is equal to root. Next, check if the binary tree is empty. It is empty. Okay, how will you know if the binary tree is empty? To the root. If root is equal to null, then return true. Otherwise, return false. Okay, next, we have to implement the traversals in order, pre-order, and post-order. Okay, pass the root And then it will not stop until the root is null. So if root is not equal to null, so magbalik-balik siya, ani. For the in order, it's left, root, right. So in order, and pass the root dot left link, and okay, print lang kay para sa ma-display siya in a horizontal line. We will print the root.info. Next, we will traverse the right. So in order, root.right link. Okay. Next, for the post order and pre-order, okay, pare-parehas gihapon ani, but ang iyahang sequence lang. Pre-order, and we have the BT node called the root node. If root is not equal to null, so pre-order root left right. So we have to print the info first. Root.info plus the space. Next, we have to traverse the left. Root.left link. Then traverse the right using the root.right link. Then the post order traversal. Okay. If root is not equal to null, then post order left, right, root. So traverse the left subtree using the root.left link. Then traverse the right subtree through the root.right link, and then print the info. We have here root.info. Okay. Now, so for the insertion, for populating the tree, we have to create another class for this. Okay? Okay, this is only for the binary tree man lang. So create another class for the binary search tree class. And this one extends from BT class. So the methods of binary tree will be inherited in this class. So for this, public class BST class extends BT class. We need to have the reference of the root node, ABT node, root. And then we'll call the super constructor BT class. The ST class we have here. For this default constructor, we will be calling the default constructor of the parent class. So super call will be used. And then for the constructor with parameters, um, okay, so we'll be calling the root is equal to root. Next, now here we can insert na. How will you insert? Okay, to insert an item in our BST, we have to make sure that the left node must be less than the root and the right subtree must be greater than the root. So, for example, public void na lang, then insert. You need to have the copy of the item to be inserted of type integer. Okay, item. Then you have to create an instance of the node. New node, BT node must be small o. New node is equal to new BT node. Next, we have to set our new node dot in left link is equal to null. Then new node dot info is equal to item, and you know that right link is equal to null. Okay. Then we have to traverse the list or traverse the tree. Okay. So to traverse the tree, we need another reference variable of type node, like current. Okay. So if root is equal to null, then we will point the root to our new node. Else, we have to look for the location on where to insert our new node. Okay, let current point to the root node. Then, while current is not equal to null, okay, so while current is equal to null, and we need another reference variable that will point to the previous node on where to insert, since a movement will be used if the position that we are going to, where are we going to insert our new node is not empty. So there are movements na mahitabo. So for this, we need to have another reference variable of type node like trail and initialized to null. And here, while current is not equal to null, okay, we will be tracking the node using the trail, and now it will point to the current. Now, if um, item is equal to the current.info, so kinahanglan dili mo repeat ang item, dili mag-duplicate ang imuhang items sa imuhang binary search tree. If item is equal to current.info, Inca already exists. Okay. Then we will, if you cannot insert an item, so we will set a Boolean variable for that. Like, for example, we'll be setting here Boolean like insertable. Okay, and it's set to true. Okay, so if the item already exists, then we will set the insertable to false. Then break. Then here, else, okay, if wala na repeat, then you have to check again. Here, we can choose now whether left or right. If item is less than current.info, then we have to look for the left. Current is equal to current dot left link. And then else traverse to the right. Dot right link. Okay. Okay. Then after that, since we have to look, we have another variable, reference variable, which is trail, that is always pointing to our current. Okay, if item is less than trail.info and is the insertable is true, okay, and is insertable, so ibutang na nato diri. Trail.leftLink will point to our newly node that we have created. Else if, okay, else if insertable, okay, if true, then trail.rlink will point to our new node. Okay. Okay. So now maka-insert na ta. So let's try to verify if the item are placed in the right place. in the right location. So we will try to implement this one. For this one, static lang sa nato ang value of the info. And here, bst class bst is equal to new bst. And then the bt, okay. Let's try to insert bst dot insert, for example, 20. Insert 20, then bst dot insert 10, then bst dot insert 30. So dapat when we have 20, 10, and 30, I will be opening a Jamboard for this, for the illustration. Okay. So when we have insert 20, 10, 30, so ang forma ana, you have here 20 as the root node since our tree is empty. So mahimo siyang root node. Then the next item is 10. So 10 is less than 20, so it must be placed at the left of 20. Then 30. So 30 is greater than 20, so it must be placed at the right of 20. So must be here. Okay. Then if naakay in order, so you have 10, 20, 30. Then, yung ka o pre-order, we have 20, 10, and 30. Then, kung maingon ka o post-order, you have 10, 30, and 20. Now, let's try to add for the traversal. In order, then wait for a while. Okay. Yun. Pre-order, we have bst.root. Then, post-order. bst.root. Let's try. Oops. Butangan sa nato og label, ha? Mhm. In order. Pre-order. Post order. In order 10, 20, 30. Pre-order is 20, 10, and 30. And post order is 10, 30, and 20. So it seems that our insertion method is correct. Okay. Okay. All right. Now, if we are going to add more, for example, we're going to 50, third, hindi na pwede ang 30 kaya ni-repeat na siya. 35. Mhm. 50, 35, and 70. And then, 5 and 15. Okay. So, when you insert 50, okay, 50 is greater than 20, and it's greater than 30, so 50 must be put at the right of 30. Next item is 35. Now 35 is greater than 20, greater than 30, but less than 35. So 35 must be placed at the left of 50. Next, okay, next item is 70. So 70 is greater than 20, greater than 30, and greater than 50. So 70 must be placed at the right of 50. Now, sorry. 70 here. And then, we have 5. So, asa matibutang si 5. So, check and compare. 5 is less than 20 and less than 10. So, 5 must be placed at the left of 10. Next, we have here 15. So, 15 is less than 20 but greater than 10. So, 15 must be placed at the right of 10. Okay. So, for the insertion, it's 5, 10, 15. Okay. So, for the newly created binary search tree, for the in order, it's 5, 10, 15, then 20, 30, 35, 50, and 70. Okay, and next, sorry, in order. And then, for the pre-order, It's root left, right. So 20, then go to the left. Where is the root? 10. Then go to left, 5. Then 15. So we are done with the root and the left subtree of 20. So go to the right subtree of 20. So in the right subtree of 20, perform the left, root left, right. So 30 doesn't have a left subtree, so go to the right subtree. In the right subtree of 30, we have root left, right, 50, 35, and 70. Okay. Now for the post order, we have here, for the post order is left, right, root. So in this binary search tree, we will go to the leftmost subtree. Okay, so we have here, in this subtree, we have to perform the left, right, root. So 5, 15, 10. Okay, next, we are done with the left subtree of 20, so we will go to the right subtree of 20. So we have 30 and doesn't have the left. So 30 doesn't have a left. We will go to the right of 30, so which is this tree. So in this right subtree of 30, perform the left, right root. Okay, 35, 70, 50, 30, and 20. Okay, so let's try to insert 50, 35, 70. 50, 35, and 70. 70. And then we have 5 and 15. 5 and 15. Save. Okay, let's try to compare if parehas ba ang ato ang result. In order, 5, 10, 15, 20, 30, 35, 50, and 70. Pre-order, 20, 10, 5, 15, 30, 50, 35, and 70. Post-order, 5, 15, 10, 35, 70, 50, 30, and 20. So we have successfully added an insert method for our binary search tree. Okay? So any questions so far? Any questions? Okay, I think everything is clear. Okay. So for the activity, you are going to implement the classes for our binary search tree. Okay, same as with this one, we have to create a node. Okay, with left link and right link, and info, and of course, the binary tree class. Okay, with the traversals and check for the binary tree is empty. And for the binary search tree, the add insertion, the insertion method. Okay. Then after that, okay, Okay.